Yeah, today we'll talk about an application of full binary trees and this is what is called Huffman coding. And this is essentially a coding algorithm. Let us take an example, okay? Suppose we have eight letters of the alphabet. Suppose I have A, B, C, D, F, G, and H. How many bits? How many bits would we require to encode? I'll tell you what I mean by this, okay? Let us say I have a sequence of letters that need to be, I want to transmit a document on the wire. Is let me take something. Able was I saw L. Let's say I want to transmit this on the line. Okay. So what do? I replace, we use what is called ASCII, which is the American Standard Code for information exchange. Okay. But what this does is, so ASCII, there is something called 7-bit ASCII. There is 8-bit ASCII. We use additionally a parity. And then there is also something called ISCI, Indian Standard Code for Information Interchange. This is Indian Standard Code for Information Interchange. Now, what do these coding schemes do? These coding schemes are what are called fixed length coding schemes, and for example, space is represented by 32. Then I think the letter A is 65, and so on. Okay, and these are the code values. These are all code values. Also a code value that ranges from from 0 to 127. Okay. But these coding schemes are good. So basically, if I look at this able was eraser alba, how many characters are there? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. Okay. And if there was a full stop, I would have 24 characters. So let us say, let us put a full stop here. Let us say that there are 24 characters. Okay. So the number of bits required is 24 into 7. 7 4 are 28, 2, 14 plus 2, 168 bits of information. So this is called a fixed length encoding scheme. The question is, can we do better? Okay. Obviously, if we need to do better, we need additional information. Okay. What is the additional information? What we use is the frequency of the characters that occur in the English alphabet. Okay. I know whether you know about this. In the time of the Second World War, when it was popular to find cryptographic schemes to kind of hide the text. One of the first things that was tried was what's called a substitution cycle. Okay. This is just an aside. What is a substitution cipher? You say that you replace the letter. You randomly take you have the letters of the alphabet, A through Z, and you have another mapping, which is also A through Z, but this is randomly permutation. Okay. So if I have A through Z here, this may be W, Z, Y, whatever, A, and all the letters of the alphabet. This will also be 26. This will also be 26. So what you do is you essentially take every letter of the alphabet. So I have, let's say, an array of A through Z. If I take this able was where I saw alpha, this has W, Z, whatever. I look at the mapping from A to this. So if I'm writing able, for example, let me write only AB because I've not got the other letters. I will replace AB by W and Z. Okay, this was a very popular scheme, but it failed miserably. Despite the fact that this permutation was very bad. was quite random. Okay, failed miserably. Why so? People immediately came to know that if one knew the language, one could readily decipher this text. Why so? Because you find that the most frequent letter of the alphabet is E, next is T, next is S, and so on. So if it's a long message, in short messages don't make much difference. If it is a long message, all that you do is replace the most frequent letter, from that permuted list with the most probable from A through Z, and so on. The best part is you don't really need to do too much work. Let me give you an example. Suppose I told you something like this. I can quickly figure out that even though I have not filled in the vowels, you can say that this is a book. And on the other hand, I give you sorry. Something like this. This is very difficult to figure out. Okay. What I'm saying is, like this, you have a list of words in your dictionary. This is a word in your dictionary. This is a word in your dictionary. In the language English that you know that these words occur in your dictionary. And here, on the other hand, because there's too many only vowels are filled, it's always much easier when you have consonants. Still, you can fill the consonants, but you can't fill the vowels. In fact, as anecdotal as it may seem, it's very interesting in speech recognition. We use the vowels rather than consonants to decipher what the sentence may be. That's a different problem altogether. Okay. So what it tells us is that if I know the frequency of the letters of the alphabet, I can, whatever random permutation I will fill it. On top of it, I have a dictionary in my brain. And even if part of them are filled, I can always fill the rest. So this was the idea, and they found that. So basically, what people used was the probability of occurrence of the letters of the alphabet. And what is its relation to Huffman coding? Huffman came up, he did this at part of the master's thesis, master's project, actually, course project, came up with an algorithm algorithm that will reduce the required number of bits for representing a code word for each letter of the alphabet. Okay. It is not a fixed length code. It's called a variable length encoding scheme. Okay. Let's see how this algorithm works. So what he hypothesized was that a letter that is very frequent must be represented by fewer bits. Okay. So that was the idea. So if we know the probability of occurrence of a letter or of the letters of the alphabet, we can build a good code. We can build an optimum coding algorithm. Okay. And how does it work? Let us take this example that I have. Yeah. What we do is, let us say we have the letters of the alphabet A, B, C, D, and E, and these occur with probabilities 0.12, 0.33, 0.15, 0.08, and 0.32. What we do is, initially, we store these values in an array. I'll go with the algorithm and then we will discuss this. Okay, only 5 letters. You can do it for any number of letters. In fact, Huffman coding is so popular, it's used in images also for JPEG and so on. So what we do is we create what is called trees. This is an array. Each element of the array stores the probability and the letter. C. And G and 0.32 E. This is actually called a forest. we create what's called a forest of binary trees. Why do you call it a forest of binary trees? Because each tree is independent initially. So what is this? Each tree has at its root the letter A and 0.12 like this. B, similarly, B 0.32 and so on. C, so it's a single root node and so 0.15. So let's do this Huffman coding algorithm. As I said, we start with a forest of binary trees. And each, that means what is a how do you represent a forest? It's essentially an array of binary trees. Okay. Now, what we do is, this way this algorithm works is as follows. So what do I have? I have the letters A, B, C, D, and E, which are in their own binary trees. It's like this. Okay. Single node. Okay. Single root node, and that's it. Then these have probabilities 0.12, 0.15, 0.08, and 0.32, 0.33. So we take the nodes with the lowest probabilities. So this will be 0.12 and 0.08, and this becomes 0.2. So now let me, so what did we have? We had 5 trees, and the 5 trees become 4 trees. 5 trees become 4 trees. So once again, I can make a table, and on this table, I have the letter A, which is pointing to 0.1. I'm sorry, I have the letter B now because A has got merged. I have here a pointer that says this is 0.2, and there are 2 children, A and B, to this. Then I have the pointer B, 0.33. It still has only B this, and 0.15 with C, which has only 1 node. And then I have E with 1 node, 0.3. Okay. Now, what do I do? This is 0.33. Then among these, I choose the smallest. So what do I have? 0.22 and 0.15 will be merged. So when I merge both of them, what do I get? I get a new table, again, or a new forest with only 3 trees, where I have 0.35, 0.33, I'm sorry, 0.32 and 0.32. Okay. So now 0.35 points to what now? It points to what bad 0.2. So I have the C, and I have sorry, this is 0.35, and this is 0.2, and I have, it's again still a full binary tree. I have A and B over here. Okay. Then Among these two are the smallest. So I have three binary trees from 3, and these are 0.33. B is in its own tree, and E is also in its own tree. And finally, what do I do? I merge the smallest probability trees again, and I have 0.35 here, which is this tree that we have, and the other one. Now these two are merged. So I have only one single tree, 0.2 single tree, two trees, with here B and E being merged. And finally, I merge it, whatever here. I merge these two, and what do I get? I had A, B, so I had A and B. Then I had A, B, C here, and then we had, when we merged these two, I had B and E over here. Okay. So then what I do is, that means what? I keep processing this until it becomes, until I have a single tree. I have only one tree. Okay. Then notice that it is a full binary tree. Every internal node has two children. Then what I do is I assign weights, or I assign 0, 1, 0, 1, 0, 1. There's no sanctity about putting, you can put 0, 1 on this branch, put 1, 0 on this branch. It will not matter. Then what we do is we start from the root of the tree, go down till we reach the leaf node, and that is the code for A. So if I complete this, what do I see? I find the code for A is 0, 0, 0. Code for B is 1, 0. Code for C is 0, 1. And code for D is 0, 0, 1. And code for E is 1, 1. Okay. So now suppose I want to transmit A, B, C, D, A. I transmit 0, 0, 0, 1, 0, 0, 1, A, B, C, D, A, 1, 0, 0, 0, 0. Notice that, so this is what will go on your transmission line as a skewed bit pattern. This can be a continuous string, depending upon what you want to transmit. So the question is, how do we decode? For example, since there are 5 letters, if I had not known the probabilities, I would have required 3 bits to represent. As somebody rightly pointed out, log of n to the base 2, take the roots of it, and this will be 3 bits. Okay. Then when it's 3 bits, for example, I could have assigned a code like this, which says A is 0, 0, 0, B is 0, 0, 1, C is 0, 1, 0, D is 0, 1, 1, E is 1, 0, 0. Okay. And all that I did was, if I'm transmitting the same thing, it should have been 0, 0, 1, 0, 1, 0, 0, 0, 1, and 0, 0. So this code, which is a fixed length code, is very easy to decode because I divided this tree into 3 bits and decode. But clearly, I don't have boundaries between the characters. So how do we decode? The way we do it is, as soon as you see the 0 over here, it starts from the root of the tree. This is 0. Then you see the next 0, go down the next branch, which is also 0, and the next branch, which is 0. Then when you reach the leaf node, you're done, and we say the decoding is A. Then next, what do I have? I have 1 and 0. Okay, so this is the next letter B, and I have next 0, 0, 1, and this is the next letter. I'm sorry, I have 0, 1, and this is the next letter C. This is done, this is done, and then I have again another B over here. So what do? I have 1 0 1 0 and finally 0 0 0, and I can decode the entire stream of symbols that I have. It's important to realize that this decoding scheme here, these symbols, for example, need not necessarily be just letters of the alphabet. It can be anything. Okay? It can be any set of symbols, and it's actually used in JPEG encoding for images too today. It's extremely popular encoding scheme for encoding various kinds of symbols. Okay? We forgot to compute the average code length of the Huffman code. And what is this? This we got 3 for A. So it is summation I equal to 1 to 5 Pi Li, and this is equal to 3 into 0.12, and B is 2, so 2 plus 2 into 0.33 plus 2 into, what is it, 2 into 0.15, plus these 3 letters plus 3 into 0.08 plus 2 into 0.32, and this total comes up to be 2.2 as pointed out by Suhas during the class. So the average code length is 2.2 for this Huffman. Okay. Okay. Now, the important point is that, as I already mentioned, the symbols can be anything. It's extensively used Huffman coding algorithm. It is considered the most optimal coding algorithm, and the average code length is actually related to the entropy of the system, and which is given by a summation of pi log, right? And it can be shown that this Huffman coding actually reaches this entropy very closely, and entropy is the disorder that is there in the system. Okay. So this is a very, very popular coding scheme, and other things about the Huffman coding algorithm, I already mentioned JPEG, where it's used. It's used in speech and used in images. Even today, a very, very popular encoding algorithm for representation. Now you can also do other things with this. Notice that when we are computing these trees every time, to find the minimum, it's like maintaining what is called some kind of a sorting order. We will learn something called min heap, which is a complete binary tree, and we will see how Huffman coding can benefit from the min heap for representation of the data. Okay? And what is the philosophy of this? What is the idea behind this algorithm? This coding algorithm. What's the idea behind this coding algorithm? We essentially coding algorithm symbols with low probability have longer code words. Okay, that's the most important property that we see here. Let me take one more example. Suppose, for example, I had A, B, C, D, E with probabilities 0.5, 0.3, 0.1, 0.05, and 0.05. We will get a tree like this. I start with these two nodes, D and D. I've just put it conveniently over here. This is 0.1. This will add to this. This will be 0.2. And I have 0.3 and 0.5. Add to this, I have 0.5 here and 1 over here. So what do I have? Look at the leaf node over here. A is represented by 1 bit, B by 2 bits. Sorry. 0, 1. There's no sanctity. You can put any symbol to any branch. As long as on one branch you put 0 and the other one you put a 1. Okay. So now what do I have? A is represented by 0, B by 1, 0, C by 1, 1, 0, D by 1, 1, 1, 0, E by 1, 1, 1. Okay. So it's very interesting. And you can see that this is again a full binary tree. So let's go back to the algorithm again. What do we start out with? We start out with a forest of binary trees. So each symbol is in its own binary tree. Okay. Only a single node is there. Okay. There's only one single node in the binary tree. Okay. Be here and see the E. All right. So we start with nodes being in their own binary trees. So notice that all these trees are independent essentially, and this is called a forest of binary trees. How do we represent it? We represent it by an array of binary trees. And how does the algorithm work? It starts by merging the two trees with the smallest probabilities. And so what happens? We started with 5 trees, it becomes 4 trees. Then it becomes 3 trees. And finally, there's only 1 until you reach it, become a single tree. So that is the complete algorithm. Once I have the complete single tree now, I take the branches and assign weights 0, 1, 0, 1 on either side, and then read off these symbols. Okay. What will happen is, suppose you did 0, 1 here and you put 1, 0 here. It's just that the code may differ, but it will still be a, be a code. For example, nothing prevents me from I add 0, 1 here and then I put 1, 0 here and 0, 1 here. I can do anything. It does not matter how you assign them, but what will happen is it yields for you a code which is a prefix code. That means what? No code is a prefix of the other. So if something is a prefix of the other, it becomes difficult to complete. That's the important point about this Huffman tree coding algorithm. We will stop here and